Thank you very much for introduction and the invitation. Today I would like to explain K-semistability of Calabi-Yau fibrations over curves. So this talk consists of three topics. The first one, I'd like to explain the background and the history of K-semistability. And secondly, I'd like to explain the definitions of adiabatic K-semistability, which is some kind of K-semistability of algebraic fiber spaces. And finally, I'd like to give the proof of our main theorems and application to moduli theory and uniformity of adiabatic K-semistability. So first, let's recall the history of K-semistability. K-semistability was introduced to solve the following problem in Kahler geometry. So we have to characterize when the polarized variety XL has a constant scalar curvature Kahler metric omega in C1L. This problem was solved for the case when L equal to Kx by O1 and Yau, and Kx equals 0 case problem was solved by Yau. So in these cases, there is a unique Kahler metric, but for Fano for the Fano case, this problem is much more complicated. Indeed, a 1-point blow-up of P2 has a non-reductive group, non-reductive automorphism group, but a Kahler-Einstein manifold has a reductive group by the Masafumi theorem. So 1-point blow-up of P2 has no Kahler-Einstein metric. So in the final case, this problem is much more complicated. But K-semistability was introduced by Jian for Fano varieties and also in general cases, which is a notion of pure algebraic geometry. And YTD conjecture predicts the following. The XL is K polystable if and only if there is a cscK metric. There is a cscK metric. So this means that the existence of a cscK metric is purely algebraic condition if the YTD conjecture holds. And this conjecture was solved by Chen, Donaldson, and Tian independently. But YTD conjecture for the general case is still open. And next, I'd like to explain the definition of the Donaldson stacking invariant and the non-Archimedean J functional. A test configuration corrects carry L for polynomial pair X delta L is a flat, proper, semi-ample, and C-star equivalent family over C. Delta means Q value divisor. So this is a codimension 1 subvarieties with rational coefficient. So, and C-star equivalent family over C with general fiber XL. So carry X looks like as follows. So and over punctured curve, this looks like x times gm, but central fiber generates in general. And by the technical reason, we may assume that Kahler X is normal. And we can set the Donaldson stacking invariant as follows. So this n plus one dimensional intersection number. And here, we assume that Kahler X is compactified in the canonical way over the point of over the infinity point. And in a similar way, we can define JH functional. So let H be a line bundle and the non-Archimedean JH and a non-Archimedean functional of Kahler X Kahler L as following n plus one dimensional intersection number. And this was solved by and next we define K-stability and J-stability. So X delta L is said K-semistable if the Donaldson stacking invariant is non-negative for any test operation. And X delta L is uniformly K-stable if there exists some epsilon such that the Donaldson stacking invariant is at least epsilon JL for any test operation. And we can define J stability in a similar way. So here JL is a non-negative functional and it's called a norm in the sense that JL equal to 0 if under if Kahler L is ample, and then Kahler X Kahler L is isomorphic to trivial test operation, which is a product with the trivial GM axiom. To experts, JL equal to INA minus JNA. This was introduced by Buxton, Hisamoto, Johnson, and minimum norm, which was introduced by Dervan. And we note that the Donaldson stacking invariant can be decomposed into the summation of the non-Archimedean entropy and JKX plus delta non-Archimedean entropy as the multifunctional. And HNA is closely related to the log discrepancy in MLP. So to state this, let us recall the definition of singularities. Let X delta be a log pair and F be a prime divisor. Prime divisor over X means for some variational projective morphism, Y to X, such that F is a prime divisor on Y. The log discrepancy of X delta with respect to F is X delta F, which is the coefficient of this divisor with respect to F. And then we can define X delta is countable terminal as the positivity of any log discrepancy for any F, and log canonicity for as non-negativity of log discrepancies. And then we can define the log canonical threshold as follows. So this is the supremum of such T as X delta plus TD is log canonical. And we have to remark the following proposition holds. If Kahler X has a reduced central fiber, then the Donaldson stacking invariant can be decomposed into the summation of non-Archimedean entropy and jkx plus delta energy. And Hn delta is expressed as follows, where V is a restoration of order E or to 5/1. So this is isomorphic to X. So Hn delta is closely related to the log responses of X. So if the YTD conjecture holds, and if we know K-stability for concrete varieties, then we would get a cscK metric on the variety. So I think characterization of K-stability or to find explicit or useful criterion for K-stability is important. First, Odaka showed the following theorem. Let X be a polarized variety. If X is not canonical, then XL is K unstable. So this theorem says that the singularities of MMP are closely related to K-stability, and Odaka also showed that algebraic geometric counterpart of Yau theorem and Oban and Yau theorem. So if Kx equal to 0 and X is countable terminal, then XL is K stable. And if L equal to Kx and X is log canonical, then XL is K stable. But for the Fano case, the problem is much more complicated as the YTD conjecture. But Vishita and Odaka introduced the delta invariant, which depends on Weaver model program. But Bram and Johnson showed that delta invariant completely detects the K-stability for Fano varieties. This means that X minus Kx is K-semistable if and only if the delta invariant is at least 1. So, and delta invariant is very helpful to construction of K moduli in algebraic geometry. But for other polarized varieties, are there any simple or useful criteria for K-stability? For example, Calabi-Yau fibration, Fano fibration, and blow-up. These structures appear in variational geometry and classification of higher dimensional varieties. For example, eta fibration and multifibration, etc.
Are there any results for the piezo surface?
Pardon? Sorry.
Are there any results in the case of dimension 2, for example, del piezo surface?
Surface?
Del piezo, Fano surface.
Face. So,
Fano surfaces.
Fano face.
Surface.
Yeah.
Sorry. Surface?
Yeah, surface. Dimension 2.
Dimension 2. Okay. So you mean?
So in the case when minus Kx is ample.
Minus Kx is ample.
Yeah.
So you mean delta surface?
Yes.
So your question is on K-stability for derivative surfaces?
Yes. Well, there is a classification of Kahler-Einstein metrics in that.
Ah, yeah. So you mean we can classify all K-stable derivative surfaces? So classification of
but I just want to see when the surface is stable or is K-stable or not K-stable in the case of minus K example. Because
so drop. So um
Yeah.
um sorry, I couldn't catch you.
okay.
Okay, maybe we can go on.
Sorry. Yeah. So we have to recall the study on cscK, the existence of cscK programs on fibrations in Kahler geometry. Phi and Dervan-Sektnan studied existence program for smooth fibration of polarized smooth varieties whose fibers and the base have the discrete automorphic groups. If F satisfies the certain condition, for example, F has optimal simplex connection, and all fibers have cscK metrics, then x epsilon h plus L has a cscK metric for sufficiently small epsilon. But this theorem can be applied to the case when all fibers are smooth. So, but Jian-Shi-Song theorem can be applied to fibrations. In the case when F has singular fiber. So the first theorem, let F be a fibration of a curve such that Kx is ample, and base is a curve. Sorry, and then x epsilon Kx plus L has a cscK metric for sufficiently small epsilon. And F is a Calabi-Yau fibration. This means that Kx is product of the line bundle on the base. If Kx is a product of L, then x epsilon h plus L has a cscK metric for sufficiently small epsilon. And this corresponds to adiabatic testability. And let me explain the proof of the Jian-Shi-Song theorem. Jian-Shi-Song utilized the Chen theorem, so we have to show that the Mappage functional is coercive, and they decompose the Mappage functional into m equals to h plus j minus reach. So this means that entropy and j minus reach energy. And Gao-Chen, Data-Pingali, and Jian-Song showed that relativity gravity conjecture. So let XL be a polarized variety H is an ample Q-line bundle. Suppose for any p-dimensional subvariety V, if this inequality holds, this J functional is coercive. And for singular variety X, this condition is equivalent to uniform J stability. So this theorem is powerful since so we can detect J stability without checking all test operations. And K-Jian showed that let delta XL be the delta invariant, which we will give the precise definition right there. Then entropy is at least delta times I minus J plus O1, some constant. And now we can define we can show some extension of Jian-Shi-Song theorem by applying J stability result. So this is an extension of Gaussian theorem only in the surface case. Let XL be a polarized surface and H be a pseudo-effective divisor. Then XL is J semi-stable if and only if this divisor is NF. And this is proved in a purely algebraic way. And stronger than the Shishon-Chen theorem in the surface case. And since H is assumed to be pseudo-effective but not ample. And then we can show the following theorem. Let F be a fibration over curve such that Kx is relatively ample and dimension X equal 2 if the square of Kx is positive, then X epsilon Kx plus L is uniformly adiabatically K-stable for sufficiently small epsilon.
Excuse me? So when you say it's stronger than Chen's theorem, it's because you consider H pseudo-effective and 2HL, L squared, I mean, it's H nef instead of ample.
Yeah, so
or is there something else?
Yeah, so Shishon-Chen theorem shows that H is ample, and so his original statement is
ample also, right?
This is ample, and so J functional is coercive.
Right.
And by limit argument, so H is nef. So by Shishon-Chen theorem, so we can show H is nef, and sorry. So yeah, but there exists pseudo-effective but not nef Q divisor. So I think this theorem is so stronger in the sense of J stability. sorry.
I understand better, so you can go on. Thank you.
Oh, okay. So, and this theorem is a little stronger than Jian-Shi-Song theorem since Kx is relatively ample. So there is a fiber surface with a relatively ample Kx and with a -1 curve. So the point of this theorem is Kx is relatively ample, but not ample. But we can show x epsilon Kx plus L is uniformly adiabatically K stable when Kx, the square of Kx is positive. And let me explain the proof of this theorem. Let me explain this proof of this theorem. It suffices to show that.
Sorry, I have a question. So
okay.
If Kx is relatively ample, so I think it's not. So because it's relatively not, and if there are no -1 curve in the fiber, so there are no -1 curve in the surface, right?
So you mean?
So how we can find -1 curve?
Yeah.
So for your example.
For example, so yeah, so this is a roughly idea. So x and Kx, but we take some pensive but base point. So we obtain a rational map and draw up and this is an example, I think. So,
but I think it is a theorem. So if for the case of fibrate surface, if Kx is relatively ample, if relatively not, it implies is not. So there are no -1 curve in the horizontal sense.
Yeah, horizontal sense.
Yeah, so your example doesn't work.
Does it work?
Because you say that it exists x with Kx relatively ample with the -1 curve. And I don't think that works.
Does it work?
Because it is a theorem. So if Kx is relatively not for fibrate surface, so it implies that it's not.
So you mean, so you worry about so yeah, -1 curve horizontal. I think this y is this y has only -1 curve, horizontal -1 curves. So I think it does not matter.
Okay, maybe we should go on.
Okay. So it suffices to show that this line boundary is nef and Kx is big note that kx over p1 is nef by Fujino theorem, and thus it follows that kx is big from this inequality. This is a kind of series criterion for bigness. On the other hand, this line bundle is ample since kx is relatively ample, and this is this ample line bundle, but this is very big. So thus x epsilon kx plus L is JK stable. And we can prove K-stability of KLT minimum models in the same way by J-stability. Similarly to the way of Jian-Shi-Song and Dervan-Sektnan. And Dervan and Ross showed some necessary condition for adiabatic K-stability. So they showed that let F be a fibration polarized varieties if x epsilon aH+L is K-semistable for sufficiently small epsilon, then the base is twisted K-semistable in some sense. LCM is the same line bundle. And in today's talk, we dealt with the following questions. Is there any algebraic geometric criterion for K-stability of fibrations? And when, and in particular, when Kx is non-nef, does Jian-Shi-Song theorem hold? So in Jian-Shi-Song theorem, we assumed the Kx is nef. But rationalized surfaces, this is a kind of a Calabi-Yau fibration, but Kx is not nef. So we have to study Calabi-Yau fibrations and obtain the partial consequences. We will explain next section. So yeah, next I'd like to explain the definitions of adiabatic K-stability. So, adiabatic K-stability means for any polarized algebraic fiber space, adiabatically F is adiabatically K-semistable if x epsilon aH+L is K-semistable for sufficiently small epsilon, and if only adiabatically K-stable if there exists delta such that the Donaldson-Stack invariant is not at least delta times norm for any test operation and for sufficiently small epsilon. In the definition, adiabatic stems from the adiabatic limit argument that Fano and Dervan-Sektnan use. And we have to also introduce the definition of logistic K-stability. A quadruple XBTL is a logistic pair if XBL is a polarized log pair and T is a Q-line bundle. And log-twisted Donaldson-Stack invariant of X L is the following the summation. And now we define XBTL is K-semistable if the Donaldson-Stack invariant is non-negative for any test operation, and uniformly K-stable if there is positive epsilon, such that the Donaldson-Stack invariant is epsilon none, at least epsilon none for any test operation. And if B equals to 0, the logistic K-stability coincides with twisted K-stability introduced by Dervan. And we want to compare adiabatic K-stability of Calabi-Yau fibrations and the logarithm K-stability of the base. To do this, we have to explain the notion of the canonical boundary formula. So let Fx to C be a Calabi-Yau fibration, and X is commutative terminal. Then the canonical boundary formula holds as follows. So Kx is the fullback of Kc plus M plus B. But B is called the discriminant divisor, defined by multiplicity of B at P is 1 minus LCT X F star P. So B counts how singular the fibers are. And M is a modular divisor. Defined to, so M is designed to, this equation holds. And for example, canonical boundary formula is coincides with the well-known polarized canonical boundary formula. Let F be an elliptic surface and J be the J function. J function means a point of C corresponds to the moduli of elliptic curves. And then the canonical boundary formula is the following. And if X is a rational surface without normal fiber, then the degree of this is 1. And for example, it is known that there exists a rational surface X with 2 star and 2 type fibers, that J is a constant. And X is GIT unstable in the sense of Miranda. But in fact, this elliptic surface is K unstable. Sorry. Okay. So then the base is the following logarithm pair. So this we can consider this as a log pair, but this pair is Fano but K unstable since the delta invariant is less than 1. And it seems to be that X is K unstable. So our main theorem states that this X is indeed K unstable. So the first one, let M and B be the moduli and the discriminant divisor respectively for KLT trivial fibration. If F is adiabatically K-semistable and M is Q cavity, then CBML is K-semistable. And the following is a partial converse. Suppose further that C is a smooth curve. F is uniformly adiabatically K-stable. If and only if CBML is uniformly K-stable. And finally, we talk about the proof of our main theorems. So the first one, we have to show if there exists a normal test operation for CL such that the log-twisted Johnson-Tyke invariant is non-negative, we have to construct a destabilizing test operation for the total space. So assume that this morphism exists. By using MMP, So the proof depends on MLP and purely algebraic way. But we construct the test operation carry x carry h as follows. So and k carry x over p1 is carry x carry c is also almost Calabi-Yau fibration. Yeah. And scalar curvature can be approximated to the scalar curvature of the base. And k carry x over p1, k carry x over p1 is this. So we can concretely calculate the Donaldson-Stack invariant of the total space by using the log-twisted Donaldson-Stack invariant of the base. So indeed, the leading coefficient of the Donaldson-Stack invariant is smaller than or equal to this invariant. So thus we could construct a test configuration destabilizing carry x h plus m ml. So we are done.
What is it you call F, EFF in the formula for?
EF. Yeah. So this minus F is effective divisor. So yeah, so this is a technical term. So if so this M is stable under base change, then this term vanishes. But if M is not stable under base change of C, then this effective divisor appears. But this is this term is anti-effective. So the leading coefficient is so smaller than or equal to this term.
Okay, thanks.
Thank you. So yeah, and to prove theorem 2, we have to recall the definition of the delta invariant. So let D be an M basis type divisor. So this characterized as the average of a basis of H0xML as this. And we can define the delta M invariant. This is the infimum of LCTXD, where D runs over all M basis type divisors. And Fujita and Odaka defines the delta invariant to be limit supremum of this. But Brown and Johnson showed that this limit supremum is indeed the limit. And for delta invariant, we have to remark the following. So let CBML be a log test pair, then HNAB non-Archimedean entropy is at least delta times norm. This theorem is algebraic counterpart of K-Jian theorem. And if L equal to minus Kc plus B plus M, so this means and M is semi-ample, so this means log twist Fano pair. So delta invariant is bigger than or equal to 1 if CBML is K-semistable. So this corresponds to delta invariant criterion for Fano pairs. So delta invariant. So by this proposition, delta invariant is also important for other K-stability for other polarized varieties. So we want to check the delta invariant for the total space, but we can prove the convergence of the delta invariant of the total space to the delta invariant of the base curve adiabatically. That is, let F be a fibration such that the dimension of C equal to 1, and B is a discriminant defined as LC trivial fibrations. So then the limit of delta invariant is the delta invariant of the base. So for any basis type, so for fiber surfaces, for any basis type divisor D in epsilon aH+L, so the horizontal part is very small. So we can dismiss the horizontal part, and for sufficiently small epsilon, we have to calculate LCT x dV, but dV is very close to the n basis type divisor of the base. So we can show that this limit coincides with the delta invariant of the base. So now we are ready to show the theorem 2. Suppose that C is this is a restatement. Suppose that C is a smooth curve. Calabi-Yau fibration is uniformly adiabatic K-stable if on the reef. The base is uniformly K-stable. And it's sufficient to show theorem 2 when the base curve is Royce's Fano, since when the base curve is Calabi-Yau or K-ample, the log twist canonical divisor is ample. So Jian-Shih's theorem shows this theorem. So in summarizing this, it follows from Jian-Shih's theorem. And yeah, so for only if part, this follows from a slight modification of theorem 1 and the following proposition. So let CBML be a K-semistable but not K-stable rotated one pair. Then there is this effective Q-quality divisor, such that perturbation, small perturbation is K unstable for sufficiently small epsilon. And we want to show if part. So if part means if the base is uniformly K-stable, then the total space is uniformly adiabatically K-stable. So let degree of B plus M equal to S. Assume degree L equal 1. Then CBML is Rose's case stable, and hence the delta invariant, the limit of delta invariant is delta CBL. So this means 2 minus S delta CB minus KC minus B minus M. And this is bigger than 1. So the delta invariant is bigger than 2 minus S. And by Gaussian theorem, x epsilon h plus L is just it's stable, and hence we have JKX NA carry x M is non-negative, is at least minus 2 minus S carry x carry M. So this is the Donaldson-Hattori invariant, but HNA is delta CBL carry x carry M. So we can show the Mabuchi energy, the Donaldson-Hattori invariant is uniformly positive. And we have to remark that if X is smooth, then X epsilon H plus L has a cscK metric by the result of K-Jian. And we obtain a partial consequence on YTD of rational surfaces. So let X be a smooth rational surface, S be a relatively unfluid divisor over P1, and rational surfaces have at most one multiple fiber, and let M with the multiplicity of this. Or if there is no multiple fiber, then we set M as 1. So XS is uniformly by classifying K-stability for log-test Fano curves, we have that XS is uniformly adiabatic K-stable and have cscK metrics if and if M equal 1, X has at most reduced fibers, M equal 2, X has no 2-star or 3-star fibers, M equal 3, and X has no 2-star fiber, or M is bigger than 3. Yeah. And we obtain a similar result by theorem 1. And in 5 minutes, I'd like to explain the result in the joint work with Kenta Hashizume. So we construct a modular of uniformly adiabatically K-stable Calabi-Yau fibrations over curves. So first one, this is a technical result. Fix N, U, and V. We want to bound of this data. So uniformly adiabatic K-stable K2 to fibrations, dimension X equal to N, and the push of F Kx has a degree U, and is F1 line bundle with fixed fiber volume. So we show that these varieties are parameterized by finitely many manifolds or complex spaces. And so we could show that these members can be expressed as orbifold of final type. And by constructing the moduli space for U-form adiabatic K-stable K-repeated fibrations, so we obtain the following existence result of cscK matrix. So consider FNUV. This is a member of uniformly adiabatically K-stable K-repeated trivial fibrations with some fixed numerical data. Then there exists a uniform positive constant W, such that if the volume of amplifying bundle is bigger than or equal to W for any representative, then XA is uniformly K-stable. And by K-Jan's result, this has a cscK metric. So by constructing our modular spaces, so for any member, so if the volume is enough big, so then this has a cscK metric. But we show that if the volume is enough big, then all members have a cscK matrix at the same time. So here we stop talks. Thank you for very much. Thank you very much for listening.
Questions or remarks?
Hi, I'm very interested in your result that the delta invariant on the total space can converge to some base, delta invariant on some base. But when you state your theorem, the base is only a curve. But I wonder if it's not a curve. I think it is still there.
So yeah, so for higher dimensional base case, so this is a difficult point. So we cannot. I cannot extend this theorem to the higher dimensional base case.
Thank you.
Okay, thank you.
Actually, it comes me if you can come back to the previous theorem 1 and 2, theorem 2.
Theorem 2?
Theorem 2, yes. So what is happening is you don't expect such an equivalence for higher dimension than a curve. Do you?
Yeah. I think so, but I think so. I expect I expect so. So the adiabatic K-stability of total space would be equivalent to uniform K-stability. Sorry, but I think we have to some modification of theorem 2.
And what in the end you obtain so you obtain this classification, right, of the elliptic surface. Can you show again a little bit later?
Elliptic surface? this data?
No, yeah, exactly. Yes. Okay. So for the ones the surfaces which don't have a cscK metric, do you expect that if you blow up, you could again make them K-stable or adiabatically K-stable?
This one is adiabatically K unstable, or
yeah, exactly. So this one is, for instance, adiabatically K unstable, and if you blow up the X,
So
do you think you could make it stable?
So I think yeah. So I expect that if this condition holds, I expect there is no Kahler-Einstein metric, since if rational double point RES with 2-star fiber and M equals 1, then this is K-unstable for any polarization. So I expect that so these rationalized surfaces have no Kahler-Einstein, no cscK metrics.
Yes, I agree. But what about the blow-ups?
Blow-up. So
yeah.
Blow-up. So you mean further blow-up of rationalized surfaces?
Yes.
I have no idea.
Are there any other remarks? I think it's time to thank.
Thank you very much.